All right, today we're tackling a real classic. We're diving into I.E. Irodov's legendary physics problem book, and we're going to solve problem 1.32. Now, this is a cannonball challenge that, on the surface, seems pretty simple, but it's got this awesome little secret about projectile motion baked right into it.
Here's the problem. Word for word, it asks how soon a cannon shell will hit a target that's 5.1 kilometers away, and it specifically tells us to ignore air drag. It seems simple enough, right? But like I said, there's a really cool physics principle hiding in plain sight here.
So here's how we're going to break this down. First, we'll look at the challenge itself. Then we'll figure out the right physics to use. We'll solve for the launch angle. And then, this is the cool part, we'll see why there are actually two paths to the target. And finally, we'll wrap it all up with the big physics takeaway.
Okay, let's get into it. First up, the cannon challenge. We got to organize what the problem actually gives us to work with. So here's what we've got. We know the range, that's the 5.10 kilometers, and we know the launch speed, 240 meters per second. And a super important detail, the cannon and the target are at the same height. Our mission is to find the time of flight.
All right, part 2, projectile motion. Now that we know what we're working with, we need to pick the right tool from our physics toolbox.
You know, the problem gives us this massive hint right in the text, in the absence of air drag. That's our green light to use the ideal model of projectile motion. It means gravity is the only thing we have to worry about, which, trust me, makes our lives a whole lot easier.
And this is our main weapon, the range equation. Look at it. It links everything together. The range r, that initial velocity, and the sine of twice the launch angle, which we're calling alpha. Now, here's the thing. To get the time, we first have to figure out that angle.
Okay, on to section 3. Let's solve for that angle. Time to do a little algebra and plug in some numbers.
So what we're going to do is take that range formula, just shuffle it around a bit to get the sine of 2 alpha term all by itself. Then we just plug in the numbers we know. And don't forget, we've got to convert that 5.1 kilometers into meters first.
Okay, so when you run the calculation, you get this. Sine of 2 alpha is about 0.868. Now, you might be thinking, great, just take the arc sine and we're done, right? Well, not so fast. This is exactly where that hidden twist I was talking about shows up.
So, let's dive into part 4. Two paths, one target. That number, 0.868, it's not just an answer. It's actually a clue that opens up this whole other layer to the problem.
To understand why, let's think back to our trig class for a second. Is there only one angle out there whose sine gives you 0.868? And the answer is a big, fat no. Remember this identity? It tells us that for any sine value, there are actually two angles between 0 and 180 degrees that will give you that same value. And this is the absolute key to the whole problem. It means there aren't one, but two different launch angles that can nail that target.
So what does that mean for our cannon? It means we have two completely different ways to hit the target. There's a low, direct path, kind of like a line drive, at around 30 degrees, and then there's a high, arcing path, more like a pop fly, at around 60 degrees. Both of them land in the exact same spot. How cool is that?
Okay, so we have two angles. That must mean we're going to have two different flight times, right? Let's use the time of flight formula and calculate both of them. Okay, for that lower 30-degree launch, the shell hits the target pretty quick, in about 25 seconds. That's roughly 0.41 minutes. And what about the higher 60-degree path? Well, that one takes its time. The shell stays in the air for way longer, about 42 seconds or 0.71 minutes. And here's the crucial thing. Both of these times are totally valid answers to Irodov's question.
All right, final section, the physics takeaway. So we found two answers, but what's the big idea here? What does this all really mean?
So here's the bottom line. This isn't just some weird math trick. The two solutions actually describe a real physical phenomenon. For any target that's not at your absolute maximum range, there are always going to be two angles that get you there. They're complementary. They add up to 90 degrees. You've got the fast, low line drive and the slow, high pop fly. And this Irodov problem is just a perfect, elegant demonstration of that fundamental principle.
And that leaves us with one last thing to chew on. Our whole solution was built on this perfect, ideal world with no air drag. But what happens when we step into the real world? How would air resistance change things? Which of those two paths, the high one or the low one, do you think would be affected more?
Now that's where the physics gets really interesting.